So everybody take out your whiteboards. Today we're going to work a bit more with systems of equations and graphing them. You're doing a great job identifying. You're doing a really good job identifying, if there's one solution or not, but we need to make a better connection with if there is one solution, how we find it. Okay, so you'll be doing a lot of interactive stuff today.
Right, so we have a system of equations here. We have two equations that make a system.
So grab your whiteboard. There shouldn't be conversation right now. Grab your whiteboard, go right back to your seat if you're not in it, and we're going to start with the first example.
So on your whiteboard, write if you think that this system of equations has one solution, no solution, or infinitely many solutions.
Without graphing. You can look back to your notes from yesterday that you wrote down to distinguish what has one solution, no solution, or many. It's a good idea. If you need to bounce an idea off someone that you're sitting with, that's fine too.
Okay, hold up your whiteboard when you have it. One solution, no solution, or infinitely many solutions. Yeah, that's right, one solution, no solution.
All right, so you're not graphing it, but how do we figure it out? Show us what you have. One solution, no solutions, or infinite. Now, it's a system, so you shouldn't have two answers. There's one answer because it's a relationship. We're comparing the two equations. So a system of equations is when we're talking about the relationship between two or more equations. So those two equations together form a system. And we're looking to see if the system has one equation, one solution, no solutions, or infinite solutions. Who wants to explain how they know that what they put on their whiteboard is correct? Go ahead.
I think it's one solution because like starts low, increases rapidly, and this one starts a little bit higher, increasing it.
How do you know? Think about what you're looking for. Now, I like how you're trying to visualize how the graphs would look in your head. Like similar to what we talked about with the pandas. Like, well, one of them started at a lower weight and grew faster. And the other one was more to begin with, but then didn't grow as much. Good idea to think of that in your head, especially when you do have to graph. What else are you looking at specifically to identify that there must be one solution? Do these have different slopes?
Yes.
How can you figure that out? Because the problem, the first equation is real nice. It's in slope-intercept form. Good. What do you have to do to the second equation? Okay, so what does that become?
Distributed.
Do we need to keep that as a decimal?
No.
Some of you may prefer a fraction. What is that as a fraction?
3/4.
Yeah, you could have had 1/4 times 3, which would have given you 3/4.
Okay, so
Oh.
now,
I just did that, sorry.
yeah, we kind of did that already. So now let's graph this. So we can see that this line definitely intersects.
You can graph this in your binder, it doesn't have to be on the whiteboard. Okay, it might be better to graph it in your binder so you have something to look back to, so you can see what the graph looks like.
Write down the two equations and then graph it, so you have it next to each other.
Why is your line intersected? Yeah. Okay, so how do you do why up there?
So sometimes your point of intersection may not be in that first quadrant. It may be in like the second or the third, like when x is a negative. So for those of you that like to start at the y-intercept and just like kind of move your line to the right, consider extending your line both directions because you'll start to see some of these systems intersect at all different places.
Does anyone want to come up here and graph this first line for me?
Riley's gonna do the first one.
Y plus 1/2 x plus 3.
Good.
Do we agree? What do we think? Okay. Why did you put that first point here? Yeah. That's where the line. We know that the line crosses the y-axis. That's correct. And then what did you do from there?
So I just started with 1 and started with 1 and
Awesome. Over 2, up 1, over 2. Good. And someone come to the second one for me. Alright, what do we think? Did you grab her right? Let's look. Where did she start?
started north.
Did anyone get a different line? So what did she make any mistakes then?
Well, I started at 1
Why did you start at 1?
because when I distributed 125 to 4, it would give me 1.
You scared me. Yeah, so when you distribute, you have to distribute to both terms. So this is actually a 1, which means our line crosses the y-axis where? On 1. Notice that Mrs. C just literally took that line and moved it down to 1. Why would she do that?
Because why? What was that? Did the line itself need to be changed? No, because what was correct? Yeah, the slope. The slope was right. So the way the line moved was completely correct. What needed to be adjusted? The y-intercept. So that's why we're able to just move the line right down. So do these have a solution?
Yes.
They do have a solution. Can we see it? Not yet, but if Miss K extends the lines. No, it's the other way. Yeah, they intersect up there. If we keep going with these lines, they do meet. They meet a little bit off our graph, but they do cross. Now, we may not see it right now, but how do we know for sure that they do cross? We may not be able to see it right now, but how do we know for sure that they will cross at some point? Because their slopes are different. So whether it's on our graph or off our graph, at some point, they will meet. Good.
Okay, so look at the system of equations we have right here. Y equals 1.5x equals 4, y equals 1.5x minus 2. Kevin stated that the equations in this system have the same slope. So there will be infinitely many solutions. Does Kevin's statement make sense? Yes or no? Answer on your whiteboards. He says they have the same slope, so infinitely many solutions. Oh, what do we think? Hold them up when you know. Alright, so somebody explain to me, what do you think? Do we agree agree with Kevin or no? He says they have the same slope, so infinitely many solutions. What do we think?
No, because if they to have infinite solution, you need to have the same slope and the same initial value.
Borrelio says that in order to have infinitely many solutions, repeat yourself a little louder.
In order to have this infinite solution, you need to have the same slope and the same y.
The same slope and the same y-intercept. Do these systems of equations have, this system of equations have the same slope and the same y-intercept? No. No. So, how many solutions?
No solution.
No solution. Good. Okay, so what would you do to change these equations to make Kevin's statement true? And write the equations on your communicator. So you can talk to each other about this.
You think you're getting sick? I think my allergies started to get bad again. Like just in general. I don't know, last time I thought it was allergies and I ended up having a CPAP. Yeah.
Use my arm.
You just take it. You was like ready to do it. Take it off.
I'll show you.
Are you sure?
Like I always forget like
Alright, what do we think? How can we change this system to make Kevin's statement true? What do we do?
You can change. Explain. Sorry. You can change the y-intercept to be the same.
Alright, so what did you do?
You could change it. I changed it to 2.
You changed what?
I just changed them both into positive 2.
Alright, so you changed both of them. You could do that.
Change both to positive 2, like that. Alright? So, how many solutions does this system have now?
Infinite.
Okay. Did anyone do it any differently? Subtracted. So what was your new equation? Okay.
So you like move them to the halfway point between the two lines. That works.
Alright, good.
No matter what you do, what's key? Yeah, you need to adjust the y-intercept somehow. You could have just changed the first one to a -2 or the second one to a +4. Could have moved them. But if you had these graphed, 1.5x plus 4, 1.5x minus 2, what would you have done with the line? Think about what I did during the last slide. Yeah, you would have just moved it down, and it would have gone from no solutions to an infinite number of solutions. Great.
Okay, so now let's take a look at this graph. Write an equation on your whiteboard for each of these lines.
So that top one will be line 1, and the bottom one is line 2. Write an equation for both.
Well, it could have been. Is that okay?
Dude, that looked the same.
Show us what you have. What do we think about this first one? Line number 1. What do we get? Good observation. It's decreasing. So what do we know about our slope? It's going to have to be a negative. And how are we going to write our equation?
Y equals, alright, that's a good start. Then
You just said negative x.
negative x.
Y plus 2.
That's where the.
Alright, because that is the y-intercept, but listen really carefully to what Marco says. Why is it 2?
Because when x is 0, y is 2.
Good, because when x is 0, y is 2. So now let's go to the next one.
Alright, but I'm just right, right? I got the first one.
First one's good. Second one. What can we find? We need 2 pieces of information for this one.
I can easily see the y-intercept, which is 7/2, negative.
That is not easily seen because that's not the y-intercept.
That is on the y-axis.
That's not where it crosses. It does not cross at 3.5. You can't assume that it crosses at a point. There's a way you can find it, and you have to find it. Because a lot of you put 3.5. That's not negative 3.5. Who's proven it though? Some people are saying negative 3.5. Some people are saying, well, it kind of looks like 3 1/4. Some people are saying it looks like negative 3 1/3. How do you prove it? Think back to what Marco said about the y-intercept for the first one. Why was the y-intercept 2? What did you say exactly? You knew that the y-intercept for the first one was 2 because why? Because when x was 0, y was 2. What do we know in this equation? What do you know? We cannot clearly see the y-intercept, but what do you clearly see? Gustav.
You see like the points, like where
Which coordinates do you see?
the coordinates 4 and -2.
So you see 4, -2,
Negative 3
and you see 1, -3. So what's the slope? 1/3. What does it mean for there to be a slope of 1/3? So for every 1x, we're going to go up a third for every one, because in that scenario, we went over 3 holes, we went up 1. So for every 1x, we go up a third. But here's the problem. We know that coordinate. So what's our coordinate when x is 0? If we know that at 1, it's -3, work backwards with your slope. For every 1 you moved a third. It works both directions. You're at -3. So imagine, going from this point to this point, I went up a third and over 1. So where is this point? What's my coordinate there? We know x is 0. What's y?
3 1/3.
Be more specific with the 3. -3 1/3. Now some of you had it, and when we were walking around, I said, can you prove it? That's how you prove it. You can use the slope to go backwards or forwards. You can't assume. Now some of you were like, that really, it's not a quarter, it's like a little bit more than a quarter, but I don't think it crosses halfway. So you were not wrong. It does look like 3 1/3 if you look really close. But depending on where you're sitting, it looks like 3 1/4. It looks like 3 1/2. So think about how you prove it. That one's a little trickier, but you can use the slope. And if you were using a table, the table would have worked well as well, because you would have had an x of 1 and an x of 4, and you would have just had to move back to an x of 0. You could have used the rate of change to just move backwards to where x was 0.
So what's our equation?
Perfect. Perfect. That one was tricky. We know that one was tricky.
Can we talk about the equation from yesterday?
It's like, are you saying half? Or are you saying
10
half?
We didn't get it back, the DOL from yesterday.
You got everything back from yesterday.
We did?
Okay.
Yeah, I'll write it down and we'll do it.
So,
Yeah, we'll do it. Just not the second.
alright, so look at the equations that you have. Substitute the coordinate of the intersection to both of those equations. So where the lines intersect, that coordinate, substitute the x and the y into both of your equations.
What's the solution of that system? What's the solution of that system? 4, -2. How do you know it's 4, -2?
That's when the two lines cross.
That's when the two lines cross. So using both equations, substitute in that coordinate to prove that it works for both. Like in that first equation, if you plug in an x of 4, does y calculate to -2? Everybody try that. You're substituting in the, some of you are looking around like you've never seen an equation before. We're just substituting in the values that we just identified on the board. If x is 4, y would calculate to -2. The first one should be pretty straightforward because your equation was y equals -x plus 2.
Here, sorry, I have this.
Oh, yeah.
I'm sorry, I just think.
Have we proven it yet?
So choose right before. It'll be 4. You want to do it before we have it?
Okay. Alright, let's see. So the first one, what do we do? How do we do this? We have a point, we said that the solution of the system is 4, comma -2. How can we prove it?
With the first equation,
For the first equation.
if x is 4, then -4 plus 2.
X is 4. Now we have -4 plus 2. And we replace our y with -2. What do we have? -2 and show us.
That's it.
What does that mean for that point on that line?
That means that both of them.
We're just looking at the first one. What does that mean? We plugged in that point.
Oh, that means that it's correct. Like your statements that you're making.
So where is that coordinate?
On
It's
the intersection.
it's on the line.
Oh, yeah.
We're not really talking about the intersection yet. We're just trying to figure out if that coordinate satisfies both equations. We know it's definitely on the first line because when we substituted in the values, it was a true statement. If we substituted in like 3, -2, it wouldn't have worked because 3 and -2 is not a coordinate on the line.
Alright, so now let's do the next one.
Again, x is 4, and then will be 1 1/3 minus 3 1/3, which is negative.
-2 equals -6. So we know now what? What do we know about that point on that line?
It's also
Yeah, so that's the point on that one. So we know that this point is on both of these lines.
So you just proved that 4 -2 is actually the solution to that system.
Why is it important to check your answer from the graph and the equation?
Because when you're doing things like this, like you kind of feel you're always right. 'Cause, like you can assume things quickly.
Mhm.
You think it's right, and when you graph it, it'll look incorrect.
Yeah, so some of us were like, yep, that's -3.5. Done.
And that would have changed your whole equation because that would have changed the coordinates on your line if your y-intercept was different. And it happens, right? Graphing is not easy, especially being exact, especially when you're graphing in a notebook and not on graph paper. So you use that check method with the coordinates to just make sure that you're exactly right. We don't have time for that. Yeah.
Okay. So consider this equation, 5x minus 2y equals 6. So what I want you to do is create another equation that, to make a system of equations, so create one equation that shows that that system would have exactly one solution. Create another equation to go with this one, to show that that system has no solution. And then another equation to go with this one, to show that that third system has infinitely many solutions.
So you're given the first equation of a system. You're going to create the second equation, whatever equation you want. Okay? The first time you do it, your second equation and that original one are going to make a system that has one solution. The second time you do it, the new equation is going to be paired up with the first equation so that you have no solutions. And then the last time you do it, you'll do it so your second equation has an infinite number of solutions with the first equation.
So every time you're making a new equation, or you just change.
So 5x minus 2y equals 6. Is that it? So this is what your paper will look like. So this one, you're going to make a second equation so that they have one solution. A second equation so they have no solution. And then a second equation so they have infinite solutions. Now you have enough information in your notes that kind of tells you what you know about two equations if they have one solution, no solutions, or infinite. You have that written. No, you can do it in your notebook. It's actually a really good thing to kind of talk through and have written down. I'm going to stop the timer of the video.